morning, everyone, and a very warm welcome to our annual conference. As you know, this is a very special year for CMI. This is our 20th anniversary. Of course, mathematicians like to be a little bit more precise than that. So I looked up the original articles of incorporation. It came with a certificate of incorporation, and that was deposited at 11:30 in the morning on the 25th of September 1998. That's Eastern Daylight Time. So we should properly celebrate our 20th anniversary at 4:30 tomorrow afternoon. But we are going to cheat slightly this evening in that there's a cake we should eat this afternoon. But I think that's justified because although the articles were filed on the 25th, they were actually signed on the 24th. So I think this is also an anniversary. So the theme of this year's conference is we're celebrating the work of people who've been supported by the Clay Mathematics Institute over the years or have otherwise been closely involved in things that we've done. And that, of course, is true of a lot of people in this room and not just of the speakers. The celebration is perhaps a little tinged with sadness that we don't have Landon Clay with us. He passed away last year, and so he hasn't seen this very important milestone. It's also rather sad, I think, that we don't have Marianne Merzicani. She declined our invitation to speak at this meeting on grounds of ill health not long before her untimely death last year. Anyway, CMI is now in very good hands. We have Landon's four sons, who are the directors of the Institute. That's Thomas Clay, Richard Clay, Landon H. Clay, and Cassius Clay. They are now at the helm. And as of next week, I shall be handing over to my successor as president, who is Martin Bridson, and he will take over on Monday next week. So I think we can look forward to an equally successful 20 years in 20 years' time. So I'm now going to call on Andrei Okunkov, who's going to chair today's session, to introduce our first speaker.
Good morning, everyone. It's my great honor to be serving the Institute on the Scientific Advisory and to be introducing the speakers this morning. And our first speaker, John Morgan, is a very old friend of mine. In fact, we shared an office on more than once in our career. And I've been always very eager to hear about math from him. I don't want to subtract any more from his talk by a lengthy introduction. I just want to say that John's associations with the Clay Math Institute are many, but the first thing that springs to mind are his two volumes of the Clay Math Institute, the two CMI volumes that he wrote, and in fact he was going to speak about that, about Perelman's work on geometrization of three manifolds.
Got it. Thank you, Andrei. Well, it's a great pleasure to be here. I'm very delighted and honored to be able to stand before you and talk about the solution to the one Millennium Prize problem that has been solved. Speaking for my fellow topologists and differential geometers, I feel like, as far as the Millennium Prizes are concerned, we've done our job. And now the ball is in the court of the number theorists, the algebraic geometers, the mathematical physicists, the analysts, and the theoretical computer scientists. I hope they step up their game. I would love to see another one of these problems solved before I move on to the hereafter. So I am going to talk to you about Perelman's solution to the Poincaré conjecture. Actually, let me just say one other personal word. Twice in my life, I have had this chill go over me when I heard about a mathematical result. The first was Wells's announcement of the proof of Fermat's last theorem, and that arrived to me with a real bang. I had no idea Andrew was working on this or that he was close to a solution. The second one was the Poincaré conjecture, and as you'll see in just a moment, that didn't arrive with quite the same bang. It took 6 months or a year of building up confidence that the proof was really right, but at some point I was convinced the proof was right, and I felt that same thrill and chill again. So, Perelman put up 3 papers on the archive. The first one, the entropy formula for Ricci flow and its geometric applications, 2002. He was considering what are called blow-up limits of Ricci flow. So as the Ricci flow approaches a singular time, the curvature blows up, and one tries to get a model for exactly what the region where the curvature is blowing up is. And he was able to establish a crucial non-collapsing result, which had been something that Hamilton had to assume in his work on the blow-up limits. And because of this non-collapsing result, together with what Hamilton had already done, Perelman got very strong topological and geometric results about the natures of the regions in a Ricci flow where the curvature is blowing up as you approach the singular time. But this was in the context of an ordinary Ricci flow. At the end of this paper, he states that once you have this control over the nature of the singular development, the development of singularities in the Ricci flow, you can construct a more general object called a Ricci flow with surgery that will exist for all time, that won't stop at some singular time. And he outlined very briefly how this should prove the geometrization conjecture, which includes as a special case the Poincaré conjecture. In his second paper, Ricci flow with surgery, it was posted in March 2003, so 4 months later, and as promised, he, in an abbreviated form, gave the arguments for constructing a Ricci flow with surgery and analyzing its limits as t goes to infinity and showing how that implied the geometrization conjecture. Then about 4 months later, he posted a third paper, finite extinction time for solutions to Ricci flow on certain 3 manifolds. And in that one, he gave a shortcut to prove the Poincaré conjecture, or in fact, analyzed 3 manifolds of finite fundamental group. The point being that for these manifolds, this Ricci flow with surgery, which exists for all time, becomes extinct after a finite time. And therefore, you don't have to worry about what the limits at infinity look like. So you have a slightly different and less complicated argument for the proof of the Poincaré conjecture. In total, these papers were probably 70 pages, and they were brief. This, of course, left Perelman open to questions. Well, is it really all true? If you've been through all the details. And there was a lot of back and forth about, was it proved, was it not proved? Various groups of people started collaborating, trying to work out the details of what he had sort of hinted at or given a guide to in his papers. And it took a while. Many people have asked me, well, why did you believe that Perelman was right? didn't you have doubts? Well, in the beginning, I didn't know if it was right or not, but the more I studied the papers, I had over and over again the same sort of experience. I would read a paragraph and I'd have no idea what he was talking about or how this was an argument. So I'd think about it, maybe I'd talk to my collaborator Gang Tian about it, we'd discuss it, maybe I'd talk to people in different groups, Bruce Kleiner, John Lott, about if they understood this point. Maybe I'd figure it out myself. Eventually, I would understand what the paragraph said. I'd understand the argument. And then I would think to myself, suppose I were going to summarize this argument in a short paragraph, hitting all the key points. What would I write? And that's what Perelman had written. So I was completely convinced when I had this experience about 8 or 10 times that in fact he had been through the argument down to every detail. He just, for whatever reason, had decided to write an abbreviated version rather than a complete version. There was also the feeling that, much like Hardy describes his reaction to Ramanujan's letter, a fraud could not have figured this out or made this up. This had to be a genius. Now, geniuses can make mistakes, so what worried me the most about the argument was the gap between I've made this careful analysis for an ordinary Ricci flow. Now and that allows me to do one surgery. But now I need to know that this analysis holds after I've done 1 or 2 or any finite number of surgeries to know that I can continue to do the next surgery. And that wasn't really explained at all in detail. And that is, to me, the most technically difficult part of the argument. So I was worried that, okay, you've done a special case, and then you say, it works in the general case, and here are the things you need to change. That's where I tend to make mistakes, so when I argue that way. So I felt like you had to start from the very beginning and do this argument in the first paper in the context of Ricci flow with surgery. And that took a while, but once that was worked out, then I was completely confident. Well, I'm going to try to put this result in context for you. So let's start back in prehistory, back in the 19th century. At the end of the 19th century, the beginning of the 20th century, Poincaré had a long series of papers on topology of higher dimensional manifolds. In fact, it's interesting to go back and read them. He justified why it was a reasonable mathematical enterprise to try to study high-dimensional manifolds, even though we couldn't see them. Something that seems strange to our ears today. Anyway, he concentrated after the general result about manifolds of all higher dimensions on 3-dimensional manifolds, and he asked, if a manifold has the same homology as the 3-sphere, is it in fact homeomorphic to the 3-sphere? Well, in his next paper, he introduced the fundamental group, which the French call the Poincaré's group, and he constructed a 3-manifold, now called the Poincaré homology 3-sphere, whose homology is the same as that of S3, but whose fundamental group is the binary icosahedral group of order 120. So this is a counterexample to his previous statement. It's a manifold with the homology of the 3-sphere, but because he's found a new invariant, the fundamental group, he can show it is not homeomorphic to the 3-sphere. So he reformulated his conjecture, or his question, if a 3-manifold has trivial fundamental group, is it homeomorphic to the 3-sphere? And that the answer is yes, became known as the Poincaré conjecture, though Poincaré never formulated it as a conjecture. Now, Poincaré thought about 3-manifolds in purely topological terms. He viewed them through the lens of what's called a Heegard decomposition. So you're to imagine these are both solid handle bodies, 3-dimensional solid handle bodies in 3 space. You take them and you take any homeomorphism between their boundaries and use that homeomorphism to glue them together. And that makes a closed 3-manifold. Of course, depends on the genus of the handle body, how many holes, And it also depends on which gluing homeomorphism you take. But turns out every three-manifold can be obtained this way. And there, in fact, even a sequence of elementary moves. If you have two presentations of the same three-manifold, you can get from one of these presentations to the other by a sequence of elementary moves. But like a lot of these approaches in mathematics, you have no bound on how complicated the sequence can be, what's going to happen to the genus of these handle bodies as you go through the sequence, and therefore no effective way to figure out whether or not this particular presentation gives the three-sphere. It is fairly easy from this presentation to calculate the fundamental group. Okay. So it's a very topological approach, surfaces and curves on them, to the Poincaré conjecture. And indeed, the topologists of the first part of the 20th century, first two-thirds of the 20th century, three-quarters, followed Poincaré's lead and attacked this problem in purely topological terms. The approaches there were many approaches, but they all involved moving curves and surfaces around inside the three-manifold somehow, simplifying whatever presentation you had until you reached a presentation or configuration that you could recognize as forming the three spheres. Well, these techniques made a lot of progress in three-dimensional topology, but they did not say anything about the Poincaré conjecture. But let me just introduce to you one thing that we'll need in what follows that did come out of this direct topological approach. It's called the connected sum decomposition for three manifolds. So here's a picture of the connected sum decomposition. You have some three manifold, and in it there's a dividing two-sphere. You cut the three manifold open along that two-sphere, and you get two three manifolds with boundary. The boundary of each of them is a two-sphere, and you simply cap the two-sphere off on each side with a three ball, and you produce two new three manifolds, M and N, and the original manifold is called the connected sum, denoted this way, of M and N. Now, if N is the three-sphere, it's not hard to see that the connected sum of M and N is the same as M, and vice versa. So you call a connected sum non-trivial if neither of the two sides is a three-disk, a three-ball, meaning that neither of the closed manifolds you get down here is the three-sphere. And that's what I just said. So the process of going from this more complicated manifold, the connected sum of M and N, to M and N is called the connected sum decomposition. And it's non-trivial provided neither M nor N is the three-sphere. Okay? So a three-manifold is said to be irreducible if you can't divide it up this way, if it's not a non-trivial connected sum. And in the 1920s, Knaser proved every compact three-manifold is an iterated connected sum of finitely many irreducible three-manifolds. So every manifold is made up out of irreducible pieces. In the 60s, Milner proved that two connected sum decompositions of a compact three-manifold into irreducible pieces yield the same set of irreducible three-manifolds up to homeomorphism. And one consequence of this is that if there's a counterexample to the Poincaré conjecture, then there's an irreducible counterexample. It also shows the classification of three manifolds is the integers. There are countably many irreducible prime three manifolds, and every manifold is a product, connected sum, of finitely many pieces unique up to the order of the pieces. But it doesn't tell you what the irreducible manifolds look like. There are countably many of them. Okay. Well, this topology didn't really say anything about the Poincaré conjecture. And I think if you had polled my topology friends in 1970, is the Poincaré conjecture true or false? 50-50. There was no strong reason to believe either way. There were always proofs floating around. Often there were counterexamples floating around. All of them turned out not to be correct. But the next advance wasn't directly on the Poincaré conjecture. What eventually led to an advance in the Poincaré conjecture was not directly about the Poincaré conjecture. It was about hyperbolic geometry. So ironically, this involved a different part of Poincaré's work, completely disjoint, I think, in Poincaré's mind from his topological work, and it eventually played a central role. So Fuchsian groups were understood to have deep and important connections to the topology of surfaces. Every surface of genus greater than 1 is homeomorphic to the quotient of the unit disk, or the upper half plane if you prefer, by a discrete subgroup of PSL2R acting freely by fractional linear transformations. Okay? Said another way, every surface of genus greater than 1 carries a hyperbolic metric, one that's locally isometric to the upper half plane with this metric, the usual Euclidean metric divided by y squared, or equivalently locally isometric to the Poincaré model, which is the unit disk with the Poincaré metric. So that's the picture for surfaces, and one often studies surfaces, the space of all these representations that give a different surface, beautiful Teichmuller space. There's the Poincaré model, in case you don't know it. So it's the interior of the unit disk, that's the space. The geodesics are straight lines through the central point, are circular arcs perpendicular to the boundary. The metric is a conformal metric, so the angles that you see in the plane are the angles of the metric. But of course the distance is distorted because it's an infinite distance out to the boundary. Okay. Well, Fuchsian groups were extended by Klein and Poincaré to groups that Poincaré called eventually Kleinian groups. So we replace PSL2R by PSL2C, and you consider discrete subgroups of PSL2C. They act naturally on the two-sphere by conformal transformations, and the Fuchsian groups are the special Kleinian groups that leave invariant a geometric circle or its interior, the geometric disk, and they'll act automatically discretely there and produce a surface. Some Kleinian groups have an invariant region, an open region in the two-sphere where they act discretely. Others have no such region. But it's important to think about the interior of the two-sphere. And maybe one way to introduce it is to say the group PSL2C acts as the isometry group or anisometry group of the real quadratic form with one negative eigenvalue and three positive eigenvalues. So it acts on the hyperboloid of two sheets where that form is equal to -1, and it leaves invariant the complete Riemannian metric that Q induces on this manifold, which again that's equivalent to a Poincaré model, which is the open unit 3-ball with an analogous metric to what we had in the two-dimensional case, the Poincaré metric. Okay. So that's an action of PSL2C as conformal transformations of the two-sphere or isometries of this metric acting on the 3-ball. A 3-manifold is said to be hyperbolic or have a hyperbolic metric if it has a complete metric that's locally isometric to the Poincaré model. And such manifolds come from discrete torsion-free subgroups of PSL2C. These groups act freely and properly discontinuously on the hyperboloid or equivalently on the Poincaré 3-ball. And indeed, there's an equivalence between such manifolds up to isometry with these subgroups up to conjugation. Now, if the manifold's compact, or more generally, if this complete metric has finite volume, then the associated Kleinian group has no region of discontinuity on the two-sphere. So there's no open subset on the two-sphere where it acts discontinuously. To see the discontinuous action, you have to go to the interior where you have a nice discontinuous free action, and the quotient is a 3-manifold, a hyperbolic 3-manifold. Okay. So in the late 70s, Bill Thurston began a deep and vast program of studying hyperbolic metrics on three manifolds with a focus on metrics of finite volume. And there are some obvious and necessary conditions on the fundamental group of M, and I've listed them in the compact case for simplicity. The fundamental group has to be an infinite group. Every non-trivial abelian subgroup must be infinite cyclic. The group is not a non-trivial free product, and it's not isomorphic to Z. Those are the obvious necessary conditions. Bill told me once, when he was an undergraduate, he was, even in those days, thinking about hyperbolic metrics, and he tried to put a hyperbolic metric on the complement of the trefoil knot. Now, unfortunately, he didn't realize it at the time. He didn't know, I guess, enough about the fundamental group or fundamental complement of knots. That group does not satisfy these conditions. It has non-trivial abelian subgroups Z cross Z. So that manifold has no hyperbolic metric, but he tried for quite a while to put a hyperbolic metric on that manifold. Eventually, he understood this and began putting hyperbolic metrics on lots and lots of manifolds. So Thurston was able to show that many manifolds satisfying these necessary conditions do indeed admit hyperbolic metrics. And there's one big difference that I want to point out between this case and the case of surfaces, which is, unlike the case of surfaces, this hyperbolic metric, if it exists, is unique up to isometry. And that's a consequence of a general theorem in Lie group theory called Mostow rigidity. So Thurston was confident enough to conjecture that every manifold meeting the obvious necessary conditions that I listed before, in fact, has a hyperbolic metric. So that's his hyperbolization conjecture. If a compact irreducible three manifold has a fundamental group satisfying the necessary conditions listed above, then the manifold admits a hyperbolic metric. He also extended this in the obvious way for complete finite volume hyperbolic metrics. The extended conjecture says that if an open manifold is going to admit a hyperbolic metric of finite volume, it must be the interior of an irreducible compact manifold M bar with the property that every abelian subgroup of the fundamental group that's not infinite cyclic must come up to conjugation from a boundary component. And then there are slight modifications of the other conditions that I listed before. Okay. So you could include that in his hyperbolization conjecture. Okay. So that was the conjecture. He was able to establish it in many cases that included cases about three manifolds whose structure was not known before. So he extended what was already known about the topology of three manifolds in this way. But once he believed this conjecture, even though he hadn't proved it, he asked, what about other three manifolds? Well, first thing you immediately think about is, just like in the case of surfaces, we've talked about surfaces of genus greater than 1, but there is a surface of genus 1 and the surface of genus 0, and they have other locally homogeneous metrics, the round metric for the two-sphere and the flat metrics for the torus. Well, in dimension 3, there are also other homogeneous metrics besides the hyperbolic one. There are 7 in dimension 3. There's the spherical metric, the analog of the two-sphere. There's the flat metric, the analog of the torus. Then there are decomposable metrics, two-sphere cross R, two-dimensional hyperbolic cross R, and then there are 3 others, PSL2R, a nilpotent three-dimensional group, and a solvable three-dimensional group. So those are all the geometries. So analogous to what happens in surfaces, you might think, okay, every three manifold should admit a locally homogeneous geometry based on one of these 8 examples. Well, manifolds carrying these geometries are easily classified. I won't go through the whole classification, but flat manifolds are finitely covered by the 3 torus. Manifolds of solvable type are finitely covered by a bundle over the circle with fiber the 2 torus. and the other structures give manifolds finitely covered by circle bundles over surfaces. So all these other manifolds, well, they're either 3 torus, positively curved, or they're related to 2 cross 1 or a twisted version of 2 cross 1 or 1 cross 2. So they're completely understood. But this isn't the end of the story. As Thurston knew well, not every compact manifold, 3 manifold, can have a homogeneous metric. And here's one way to construct an example. Take 2 hyperbolic manifolds of finite volume with one end. So these are 3 manifolds, and the end, analogous to what you think about for non-compact finite volume surfaces, is you have a cross-section which here is a 2 torus, and then it's exponentially decaying. Its size is exponentially decaying as you go out the cusp. Same thing here. Well, cut these manifolds off, cut off the ends, and get compact manifolds with 2 torus boundary components, and now glue them together and make a new 3 manifold, which has one piece that looks a lot like this hyperbolic manifold, another piece which looks like this one. Well, this manifold can't carry one of the small geometries because it has a subgroup. It has a subgroup which is the fundamental group of this hyperbolic manifold, much too big to be inside any of those smaller homogeneous groups. And it can't have a hyperbolic metric because here's a 2 torus carrying a z cross z in the fundamental group. Okay. So you can make many more examples of this nature. Not every 3 manifold is going to carry a homogeneous geometry. Okay? But these considerations led Thurston to formulate the geometrization conjecture. If M is a closed, irreducible 3 manifold, then there's a finite union, I called it script T, of 2 tori and Klein bottles embedded in M such that every component of the complement admits a complete locally homogeneous metric of finite volume. And if you take T to have a minimal number of surfaces in it, then this decomposition is unique up to isotopy. And as I hinted at before, if you have a decomposition like this, if you look at any component of T and look at, so let's say it's a torus, its fundamental group is Z cross Z. Under the embedding of that component into the 3 manifold M, the Z cross Z embeds into the fundamental group. The same would be true for the Klein bottle. Okay, so the geometrization conjecture is a vast generalization of the Poincaré conjecture. So let me just briefly indicate how that argument goes. So let's suppose that geometrization conjecture is true, and let's take a closed 3 manifold with finite fundamental group, and we're going to argue that it's the quotient of the round 3 sphere by a subgroup of isometries acting freely. Okay? So in the special case, if you start with a manifold with the fundamental group of the 3 sphere, that is the trivial group, it will be the quotient of the 3 sphere by the trivial group, so it'll be the 3 sphere. Okay? So the reason is, so the fundamental group of M is finite, so the family of surfaces has to be empty, because I just told you that every component has fundamental group that injects, and these surfaces have infinite fundamental group. So this decomposition in the geometrization conjecture has to be empty, and hence the manifold admits a locally homogeneous metric. But it's got finite fundamental group, so passed to its universal cover, that has the homogeneous metric. It's one of the 8 geometries we listed, and because the fundamental group is finite, the universal cover is still compact. Therefore, it's a compact homogeneous geometry in dimension 3, and if you look through the list, the only compact one is the 3 sphere. Okay. So that's how a special case of the geometrization conjecture is the Poincaré conjecture. All right, so now we set the stage, and if we poll topologists in early 1980s, I think 70-30, the Poincaré conjecture was true, would have been the result. The fact that you put the Poincaré conjecture, which is about one particular three-manifold, in a vast conjecture that's supposed to classify all three manifolds and has some positive evidence for it, makes you believe you shouldn't spend your time looking for a counterexample. Well, I think it also convinced Richard Hamilton that his work on Ricci flow, which was taking place at about the same time, might be relevant to the Poincaré conjecture. So let's talk a little bit about Ricci flow. One point, so far I haven't used a smooth structure, and I've been a little vague about what I mean by equivalence of manifolds, whether or not they're smooth, piecewise linear, topological. Turns out in dimension 3 it doesn't matter. All the categories are equivalent. And now we're going to heavily use the smooth structure because we're going to do analysis. Well, a smooth manifold has a Riemannian metric. In fact, it has an infinite dimensional family of Riemannian metrics. If M has a locally homogeneous metric, then that one is very special among the space of all metrics, and one could attempt to try to find it by a minimization process or a flow process. Maybe I'll stop here and say Thurston, in fact, tried to prove the Poincaré conjecture, starting with manifolds, or actually orbifolds, that had a hyperbolic structure, and tried to open up the cone angles on the orbifold to move to the smooth case, and began to see degenerations into lower dimensional pieces. And I remember him staring off into space and saying, you can get it a certain ways with this argument, but then it just gets too complicated. So minimization turned out, at least in Thurston's hands, not to be the way to go. And I've got to believe if Thurston couldn't do it, nobody could do it. But flow equations are much more powerful than minimization procedures. You have a lot more control. Anyway, just to continue this thought, if M has a locally homogeneous metric, maybe the flow will take you there. But what if it doesn't have such a metric because you have to cut open along tori or Klein bottles? Then maybe the minimization or flow process would develop some sort of singularities that would provide the required decomposition. And I believe this is exactly the approach Hamilton took to these conjectures. So the Ricci flow for a Riemannian manifold of any dimension is a parabolic type equation. You have a one parameter family of metrics. The time derivative of the metric is minus twice the Ricci curvature of that metric. Okay. The Ricci curvature is derived from the Riemannian curvature. In local coordinates, the Riemannian curvature is a 4-index tensor, Rijkl, skew symmetric in I and J and in K and L, and symmetric under interchanging Ij with KL. Ricci is a symmetric 2 tensor. It's the trace of the Riemannian on these middle two indices. And like the metric tensor, it's a symmetric 2 tensor. So this equation at least makes sense. On the left-hand side, we have the derivative of the metric, which is a symmetric 2 tensor, and over here we have a symmetric 2 tensor. Well, this is not an easy equation to understand, and we have this Riemannian manifold and we have this metric tensor on it, and now we're deforming the metric tensor by the curvature of space. It's a little hard to think about or get your head around, but there is a nice model to keep in mind, much simpler. Well, sorry, got ahead of myself. Let me back up. So I told you the relationship between Riemannian tensor and the Ricci tensor, but let me, in dimension 3, things are much simpler, so let me just point that out. So in dimension 3, if you're working at a point, you can find an orthonormal basis that diagonalizes the Riemannian tensor. So there are 3 indices, it's 3 by 3, and you can take it to be diagonal. In the same basis, the Ricci tensor is also diagonal, but with these eigenvalues. So you see this very special fact in dimension 3. Ricci tensor gives you the Riemannian. If you know the Ricci tensor, you know the Riemannian tensor. That's only true in dimension 3. Once you get above dimension 3, there are more variables in the Riemannian tensor than there are in the Ricci tensor. Probably the reason Ricci flow has been so successful in 3 dimensions and not yet successful in higher dimensions, though there's some work in 4 dimensions. So Hamilton established the basic properties of this flow, short time existence and uniqueness. If you have a compact manifold, Riemannian manifold as initial conditions, then the Ricci flow does exist for some amount of time, and it's unique. He also established many inequalities that have good evolution properties under the flow, and central to many of his arguments were a version of the maximum principle in the context of tensor invariance instead of scalar invariance. Now, I'm not going to go through even the most important of these inequalities, but I thought I would show you a simple inequality that's of the type that one needs. In fact, this inequality comes into the picture. We're going to consider the scalar curvature, denoted R, and by definition, it's the trace of the Ricci curvature. If you work out from the parabolic equation for the derivative of the metric, what happens to the Ricci tensor? Well, the Ricci tensor evolves according to the Laplacian in the metric, in the spatial direction of the Ricci tensor, of the scalar tensor, plus twice the norm square of the Ricci tensor. So you see, staring you in face, a maximum principle argument for this scalar function R. And standard arguments show you that if you take the minimum of the Ricci tensor, the scalar tensor at time t, so that's a function of t, take d by dt, it's greater than or equal to 3/2 the minimum of the scalar curvature squared. Okay. So the minimum of the scalar curvature is an increasing function of time. That's the first thing you see from this equation. And secondly, if it's ever positive, then it's going to go to infinity in finite amount of time. So if you ever have a manifold of positive scalar curvature, Ricci flow is going to send it, has to become singular in finite time, and you can even estimate the time from the value of the minimum from this equation. Well, there are many other equations of this type, but I wanted to show you one to give you some little sense of how all this goes. So the simpler model to keep in mind is the curve shrinking flow, which was studied by a student of Bill Thurston's, Matt Grayson, in the 80s. So here we have a curve in the plane, simple closed curve in the plane, parameterized by t, and then, curve in the plane, the parameter in the curve is s, and then we have a family of curves parameterized by t. And again, the equation is the derivative of the curve with respect to time is minus the curvature at that time, curvature in the plane. Okay. So here's a picture. So here's our initial curve. Here, why did I say minus the curvature? It should have been plus the curvature. Here are the curvature vectors. We evolve this curve using this as the first order deformation at the given point. What Grayson proved, well, if you start with a round circle and you do it, this circle, it's very easy to see. All the vectors are the same length. They point toward the center, so the circle just shrinks down through smaller and smaller circles, and at finite time becomes a point. Grayson's first theorem was if you take any convex curve in the plane and apply this flow, it shrinks in finite time to a point, and as it shrinks to a point, it becomes closer and closer to round. So if you take this right before it's a point, you get some small curve in the plane, blow it up to diameter 1, it will be approaching asymptotically the circle. Okay. His second theorem is that if you start with any simple closed curve in the plane, after a finite amount of flow, it becomes convex, and then you can apply the first theorem. Once it's convex, it flows staying convex to round as it shrinks to a point. Okay. So this is an equation you can actually visualize what's going on. And it is, from the point of view of equations, it's a similar sort of equation to the Ricci flow equation. And indeed, there are some strong similarities with the results. So let's go back to Hamilton's results for Ricci flow. If Ricci flow develops a finite time singularity, say at time t0, well, it does if and only if the sectional curvature of the metrics as you go, the sectional curvatures of the metric go to the maximum, goes to infinity as you approach this singular time. Of course, you're approaching it from below. Furthermore, Hamilton showed that if the metric has positive Ricci curvature, then the Ricci flow does become singular at some finite time. We already know that from the scalar curvature. And as t approaches this time from below, the diameter of the manifold goes to 0, and after rescaling to make the diameter 1, the Riemannian manifold converges to a round one. So this is in complete analogy to the curve shortening. Positive curvature leads to things shrinking in finite time to a point, and as they shrink to the point, they become round. Hamilton also showed, under a non-collapsing assumption, that for any finite time blow-up, say at time t0, for any finite time singularity, I should have said, say at time t0, there is a sequence of points with the times increasing and converging to t0, and positive constants that go to infinity as n goes to infinity, such that if you rescale the flow on the interval 0 to tn and you center at this point xn, and you shift the final time from tn down to 0, you get a sequence of flows from some negative time to 0, and the amount of negative time is going off to minus infinity. And in fact, these rescalings of the sequence based at xn, tn converge to a Ricci flow defined on minus infinity 0. They have non-negative curvature, and these limits are called blow-up limits associated with the singularity. So we're getting a model for what singularity development can possibly look like. We have some singularity developing at this time. Well, the curvature is becoming very large, so we blow up to bring the curvature back to a reasonable size. We get a flow defined for a larger and larger time before that, and this thing converges to a non-negatively curved flow from minus infinity to 0. All of this under a non-collapsing assumption, which I haven't made precise. Okay. So this is where Perelman enters the story. And as he himself said, he considered himself a student, albeit unacknowledged one, of Hamilton. So his first paper, which, as I said, is only in the beginning of my talk, is only about Ricci flow. There's no surgery yet. Deals with the collapsing issue in Hamilton's blow-up limits. And in fact, not only was he able to resolve the collapsing and show that there never was any collapsing in these finite time singularities, the same arguments allowed him to give a very strong characterization of the nature of these finite time blow-ups. And he found three basic types. There's a blow-up limit It's a shrinking family of round manifolds. That's the one we've already talked about. If you have positive curvature at some point, manifold's going to shrink to a point in finite time, and as it does, it becomes round. So that's one type of singularity. You can have a 2 cross 1 type blow up of the same general nature. The manifold looks like S2 cross R. The S2 eventually has positive curvature, and it shrinks to a point, but the R just doesn't, stays R. And your blow-up limit is from minus infinity to 0, a product of round 2 spheres shrinking cross R. And the third is slightly more complicated. It's where the sectional curvature is everywhere positive, and the manifold is either a 3-ball or a punctured RP in RP3, and a neighborhood of infinity looks like the model in number 2. So here's a picture of the 3 possible natures of singularity development as modeled by these blow-up models. So as our singularity develops, it becomes asymptotic to one of these 3 pictures after we rescale it. And the 3 pictures are a whole component, which is positively curved and almost round 2-sphere cross a long interval minus LL, or a positively curved piece, which is either topologically the 3-ball or RP3 minus a point with an end that looks like this model. So that's what these singularities look like. The idea in surgery, which goes back to Hamilton, he was doing surgery in dimension 4. Perelman adapted it to dimension 3. Surgery, well, it's pretty clear what to do with these components. They're disappearing anyway, so just remove them. Remove that singular point. If you have a 2-sphere cross R, you cut it open. You go out toward the ends where the curvature is not going to infinity. You cut it open, and you put in a standard cap on each end. And what you do here is very similar. You just cut this piece off out in the standard end and stick on a cap. So topologically, it doesn't look like you've done much. If this was a 3-ball, you've got a 3-ball again. If this was an RP3, well, you've thrown an RP3 away. But the point is you've changed the metric from some unknown positively curved thing to a standard cap. So this is the surgery process. You go to the singular time where the singularities have developed. If the singularity is this point, you simply remove it. If the singularity is occurring in a tube like this, you go out to the ends of the tube, which are still reasonable geometry, and you cap off. You cut open all the interior middle region that contains all the singularities in here, and you simply cap by standard caps. And here, again, you just remove this piece where the singularities are developing and put in a standard cap. So that produces for you a new Riemannian manifold at the singular time, which is topologically and metrically different from the one you had coming up to the singular time, but there are no singularities left. The flow away from these regions that we've cut out converges smoothly in the limit, and we just restart the flow again using the surgered manifold as our new initial conditions at that time, and let it go until it develops a singularity where we repeat the same process, let that one go, and just keep iteratively doing surgery every time singularities develop, because we do have the same control over the singularities for these manifolds after surgery as well as before. Okay. So that's what I just said. So in his second paper, Perelman shows that the arguments about blow-up limits of Ricci flow are valid in the context of Ricci flow with surgery, and this requires, as I said in my introduction, a rather intricate analysis And to me, this is the technically most difficult part of the work. It's not the deepest part, but it's the technically most involved part. So this allows one to continue to do surgery, and it's not too hard to see, because of the nature of what you're removing, that there can be only finitely many surgery times in any compact interval of time. And thus you can do this process iteratively, a countable number of times possibly, but continue the Ricci flow all the way to infinity. So that's a Ricci flow with surgery. Starts with whatever initial manifold you're given and goes all the way to infinity. Now, what's happened? We've changed the manifold, so we have to worry about what's the topological effect of these changes. Well, topological effect of the first change is to remove a component that emits a metric of positive constant sectional curvature, a round component. Well, those are locally homogeneous. The second was a connected sum decomposition. And the third was either a trivial connected sum decomposition topologically, or a connected sum decomposition where we threw the other component away and that other component was RP3. So it's now completely clear that if the manifold after surgery satisfies the geometrization conjecture, so does the manifold before surgery. Iterating this process from 0 to infinity, or from 0 to arbitrarily large t, we see that to prove the initial manifold satisfies the geometrization conjecture, we need only show that for large t, arbitrarily large t, the manifold satisfies the geometrization conjecture. Okay. And then, okay. So as I said, in Perelman's third preprint, he uses a beautiful monotonicity result for areas of minimal two spheres in the manifold to show that for any Ricci flow with surgery, after some finite time, all the manifolds have trivial pi 2. And a more complicated variant of this argument shows that if the initial manifold has finite fundamental group, then there's a time after which the Ricci flow is extinct. So the picture is you start with this three manifold of finite fundamental group. Under Ricci flow, well, maybe you cut it into pieces. Each piece will still have finite fundamental group. Eventually, every one of these pieces will contract down to a point and become round. But since the manifold had finite fundamental group, if you cut it into two pieces, one has to be simply connected and the other carries the fundamental group. So as these pieces disappear, all but one of them is simply a round three sphere, and the last one is homogeneous with the finite fundamental group. So that's a shortcut to the Poincaré conjecture. And let me just say a word about the more involved part of the argument. So the argument for finite time extinction is based on a functional W of pi 2 of the free loop space of the manifold. So you look at loops in the manifold, and you look at pi 2 of that loop space. It's a simple topological fact that if you have a simply connected three manifold, then pi 2 of the loop space is pi 3 of the manifold. And if the manifold has finite fundamental group, pi 3 is non-trivial. Okay, so now we have a two sphere in the loop space in the component of trivial loops. And we set this functional of a map alpha equal to the maximum over the points in the two sphere of the area of a minimizing spanning disk for the loop parameterized by that point. So we have a two sphere worth of loops. For each loop, we take a spanning disk. We take a minimal spanning disk and take its area. That gives us a function on the two sphere. We take the maximum on the two sphere, and that's the value of this functional at alpha. The value of the functional on a homotopy class is simply the minimum over all representatives of W, representatives alpha of W of alpha. And Perelman establishes a monotonicity result for W of any homotopy class, and from that he gets the extinction result. Okay, but now let's go back to our Ricci flow with surgery. not assuming we have a finite fundamental group. And let's see what happens at infinity. So this is the last part of Perelman's second paper. So as I've already said, all you have to show is that as t goes to infinity, the manifolds at time t satisfy the geometrization conjecture. So this time we look at sequences xn, tn, where xn is a point in the manifold at time tn, and the tn go to infinity. And again, we're going to rescale the metrics. And there are two possibilities. Either the sequence is non-collapsing, in which case there's a subsequence converging to a complete hyperbolic manifold of finite volume, or there's a subsequence of this sequence such that the balls of radius 1 in these rescaled metrics are collapsing to a lower dimensional space in the Gromov-Hausdorff topology, and the sectional curvatures of these balls is bounded below by -1. That may not be clear why I need what the second hypothesis is doing there, but the theory of collapsing with a lower bound on the curvature is a part of Gromov-Hausdorff theory. So in the first case, the Ricci flow rescaled and centered at these points xn, tn is actually converging to a complete hyperbolic manifold of finite volume. So we get a picture of the topology of the manifold at large time. It's a collection of hyperbolic manifolds of finite volume connected by boundary tori to regions that are collapsing. So I've tried to draw you a picture. So here's a hyperbolic piece. Here's another hyperbolic piece. These are torus boundaries. And then what's over here is collapsed stuff. We know nothing about what the metric looks like, except this Gromov-Hausdorff statement that it's collapsing to something either one or two-dimensional. Okay. But in the hyperbolic pieces, Ricci flow is converging nicely, C infinity to the hyperbolic metric. So these parts of the manifold give you hyperbolic pieces, and these parts, well, we still have to understand what they look like. But in fact, it's a purely topological argument now, not a Ricci flow or even a metric argument. If you have something Gromov-Hausdorff close to a lower dimensional space with curvature bounded below, you can prove that the pieces are either T2 cross I, so you might be connecting two hyperbolic pieces, say here, by a T2 cross I. That's one possibility. Or an I bundle over the Klein bottle. So for example, this piece might be an I bundle over the Klein bottle, or it might be something else. Or you've got things that are circle bundles over Riemann surfaces. Or you might have a completely collapsed component which would get something collapsing to one dimension, which would give you the two torus bundle over the circle. So these collapsed pieces, in fact, also satisfy the geometrization conjecture by a topological classification of these pieces rather than by any direct metric argument from the Ricci flow. In fact, in Perelman's original argument, he could not rule out that there might be infinitely many surgeries. If there are infinitely many surgeries, they're certainly not happening in the hyperbolic pieces, so they'd be happening in these collapsed pieces. In fact, it turns out that after this was done, Richard Bamler, using the full power of what Perelman did, was able to show that in fact there are only finitely many surgeries. So we can go up past the last surgery and try to study the manifold there. Its topology is not going to change as we go off to infinity. So this is how Perelman did it. And I was going to show you what I considered his main achievement, but I see I'm out of time, so I'll leave it there. Thank you.